Professor in the Department of Computer Science and Engineering at the Indian Institute of Technology, Roorkee. She holds a PhD in NLP from IIT Bombay under Professor Pushpak. She has extensive research experience spanning natural language processing, machine learning, sentiment analysis, and multimodal text generation. Her work explores diverse areas such as domain adaptation, biomedical text mining, and cause-effect extraction, with several impactful publications and a US patent to her credit. Before joining IIT Roorkee, she worked as a research scientist at the TRDDC. Dr. Sharma continues to work at the intersection of language understanding and AI, contributing significantly to both academia and applied research. We are very happy to have you, Dr. Sharma. So the floor is all yours.
Thank you so much. I hope my screen is visible. The PPT which I am going to discuss today is visible to all.
Right. Do you want to go into the screen share mode?
Isn't it a,
I have already
shared.
Actually, screen is visible, but can you open it in slideshow mode?
Yeah, can you please go in the slideshow mode? Yeah.
Is it okay now?
Yeah, that's fine. Yeah.
Okay,
thank you.
Fine. So today we will have discussion on two topics. The first one is we can say application of natural language processing, where NLP can provide solution, and which is like very well studied and open research problem statement, that is misinformation detection. And then we will be discussing like one of the possible solution. The recent techniques is transformer based model. So we will be discussing the working of transformers in detail. Let's see how much in detail I will be able to cover in this in 1.5 hours or till 5 p.m. But this content is very elaborative. I have made slides such that even if you are going through the slides later, you will be able to get the idea how transformer is working, or what is misinformation detection. So misinformation detection is also known as rumor or fake news detection. We can call them, they are brothers. There may be very fine differences, but most of the time they are regarded as the same problem statement. So whenever a news which is like false or misleading, which is not the factual statement, there can be different purposes behind sharing that news. And since when we have started World Wide Web, this has become more challenging and more important to identify fake news, because it spreads very speedily among the society or among the people. So social media portals like Twitter, Facebook, they have played a vital role in acceleration of misinformation, even if the source was one person who just initiated the news, but due to different factors. For example, I also share the same bias with the person who is source of the misinformation, or I have some links with the person, and I just follow him no matter how much biased or how much wrong he can be. I will share the information, and similarly my followers will do the same. So since when social media portals are there, one good thing is that we have enough data set available to train NLP algorithms, which was not the case before 2000, where we were dependent on rule-based systems because we were not having enough annotated data set. But since when we are having social media platforms or expansion of the use of internet, we have become very rich in terms of data set. But at the same time, it has become very dangerous when it comes to spread of misinformation. So the domains where it can create significant impact, mostly in negative direction, that is politics. So it may cause victory or fall of a particular political leader or a particular political party. And health domain, misinformation was very prevalent when we witnessed COVID time, and it may affect social harmony. So it is not limited to one particular domain. It can affect multiple directions of the society. So that is the point, that misinformation detection is very important, because it is not limited to any particular community or any particular part of the society. So it signifies that we have urgent need for automatic detection methods which can identify misinformation and immediately prompt that the posted article, or not only human beings, news channels, media websites, including international media websites like New York Times, they are sharing misinformation. Purpose can be different. They want to present some developing country image negatively, no matter what, how much good they are doing within the country, but they may portray the image in a negative manner, so that they should not be able to compete with developed countries. So what are the challenges in case of misinformation detection? So first challenge is that the amount of data and the volume is huge, and the speed with which misinformation can be shared, that is also very high. Another thing is that it can be multilingual or multimodal model data. There can be associated images. The text may be simple text, which is not much harmful, but the associated image can be more harmful. So, which is hard to detect. If we go just by the words, it may appear like simple message, which is not harmful or which is not matter of our interest, but actually that is misinformation, in we can say hidden information in the form of image. And if it is multilingual, then it is hard to decode by one language person, the person who knows, who has knowledge of one language. And it can be very sophisticated content, very well framed grammatical statement, that it is hard to be detected. And with the evaluation of such tools like deepfake, who are trained to generate such fake news, which are hard to detect, which are so sophisticated that a human being cannot identify, or cannot write himself, but a tool is able to write. Similarly, memes which appear like simple, humorous elements, but they can also spread misinformation. Another factor behind misinformation is user bias. So as I told you that if I myself has some bias, it can be for any particular gender, or it can be for any particular community. So if I myself has some bias, and if I witness any misinformation associated to that gender or associated to that community, I'm not going to verify it. I will simply spread it. I will simply forward it, because it is supporting my bias, and I was not aware of this fact that I'm biased. So I need to first correct my thinking. So there can be different reasons behind uh, generation of misinformation or sharing of misinformation, where the source himself or herself is not aware of uh, the factual quality of the, or the truthness of the content. Echo chambers. So echo chamber is very interesting terms which has actually made or created new troubles for natural language processing researchers. So echo chambers are that kind of environment where we are hearing the same news again and again. So if we hear negative statement about a particular political leader 100 times, or continuously, if we are in such an environment, suppose I am following a particular Facebook page which continuously post negative about a particular political person or political leader, then there will be a day, probably in beginning, I started with neutral mindset, but there will be a day since I'm continuously receiving those updates or those uh, uh, notifications where they are portraying the image of the person as negative image. So I may change my opinion. So that is one example of having some sort of echo chamber. And machine learning is also playing role in creating echo chamber. So we are having this recommender system. So if I'm used to following a particular type of news, okay, probably sports news or political news, then what these social media platforms will do, they will pop up such news or news from such sources which are dedicated to, or which are having some links to my previous read. My previous read may be a biased or misinformation, and the system has learned that I'm fond of reading, or I have made some attempts to read this particular kind of news, so it will again pop up similar kind of news for me. So I may be in a trap where I'm reading misinformation or wrongly portrayed image of a particular person, or a particular vaccine, or a particular drug. Okay, so echo chambers are very dangerous thing which we have encountered in recent times. Besides this, we do not have fixed boundary between free speech or the regulation which we should impose on. We cannot impose regulation on all types of news until we are, or all types of information, or all types of opinions which we are having. So we are given freedom to express our opinion for a particular political leader, or for a particular drug, what I have experienced. So, which may be considered as freedom of speech. But we do not have a fixed mechanism to put a boundary in name of regulation. Okay, so all these are actually challenges before claiming that this particular type of opinion or this particular type of news is misleading or misinformation or a rumor or a fake news. Putting this kind of label is a little challenging, even if we are putting manual efforts. So it will be more challenging for machine to do. So here are a few examples which can indicate the severity of the problem. And it is not limited to boundary of a particular country. It is like a global problem now. So in 2016, during US presidential election, there was a news that Pope Francis endorses Donald Trump, which was actually a false news, but shared by millions of users. And similarly, in Indian elections, and it is very common during elections, spreading misinformation, and it actually affects the verdict or the final result for few cases. Okay, those who are not like very attentive about the news content, they just go by the news, and it may be a fake news. So during Indian elections, there were many fake videos and morphed images circulated to mislead voters, such as altered speeches or false claims about political leaders. So these are actually links. So you can click and check the source from where it is taken. Then during COVID-19 pandemic, there was a news like drinking hot water or alcohol may cure COVID. So that was again a fake news which was published in BBC. There was another news like cow excrement, both in the form of urine or cow dung, can become a remedy for COVID-19. So this was also a news which was presented as a misinformation in a journal paper. Then there was a fake news related to polio and measles vaccine that in Nigeria and Pakistan, they claim that vaccine may cause infertility. So one should not take it. and this article was published in Nature. And there are other instances also during Russia-Ukraine war in 2022. And related, when it comes to entertainment industry, there are many fake news every next day. In fact, Amitabh Bachchan has been hospitalized, or he's facing severe disease. So these kind of fake news are very common and related to divorce of celebrities. These kind of news are very common, which are actually fake news. They do not have any base, but authentic websites like Aaj Tak or many other authentic websites which we rely on for the true news, they are also publishing such news. Yeah. So during recently during Operation Sindoor, there was in 2025 there was a news in Indian Express which surfaced online alleging severe damage to the Indian Armed Forces and the capture of military installations, the donning of fighter jets, and attacks or on prominent religious sites. So this was a false claimed which was presented and that was during Operation Sindoor, which was trying to disparage or degrade the achievements of Indian armed forces during Operation Sindoor. And there were many such news during Operation Sindoor days that we are also equally harmed by Pakistan army as we are harming Pakistan resources. So in how many ways misinformation is mostly interpreted as a binary classification problem statement? The data set can include text data as well as image data and other types of clues like emoticons or memes. They can also become part of the data. So there are 4 different ways I have broadly classified the approaches which are proposed in misinformation detection. So first is content-based detection, where we simply go by the content of the news and we try this. You can interpret as a text classification problem statement, and where NLP techniques, machine learning techniques, and deep learning techniques provide a solution. They can be directly used to provide a solution. Another approach is context-based detection. So here, what do we mean by context? We are trying to find out the behavior of the person, the behavior of the user who is posting the news. Okay, the news may be a fake news, but is it initiated by the behavior of the person, or the network with which it is associated, the person is associated? Is that an indicator of the posted news to be a fake news? So from which direction we can get clue about the truthness or fakeness of the news, we try to incorporate that into the system. So in first case, we are just relying on the text content. We are not seeing the background of the post. In the context-based detection, we are seeing the background of the person. We are seeing the network of the person who is posting the or network of the post, from where it is coming. Okay, are they very frequent? Are they very frequent in posting fake news? If they are such people or they are such network which are frequently posting fake news, then there are high chances that this particular news may also be a fake news. Then in third case, we can have fact-checking system where we are comparing the news or the claim against the fact. Okay, so if there is a mismatch, we say that it cannot be a correct news. Okay, another way approach can be knowledge graphs. So if we try to connect the component of the news with the knowledge which is available in the world, or the knowledge which is relevant to this particular news, but the knowledge is coming from the world. If we see any mismatch between the news component and the real world knowledge available in the form of graph, if this cannot be fit as a node, or if this cannot become part of this knowledge graph, then we say that news is appearing a fake news. So using knowledge graphs or fact checking system also, we can identify whether the news is a misinformation or a rumor or fake news. And the fourth mechanism is combining multiple signals. So we can combine content-based detection system, content-based model, and context-based model. And we can see improvement in the overall performance. Similarly, we can combine fact-checking based system and context-based system. So that we can say it is a hybrid approach, or combining multiple outputs to produce the final output with respect to the input news.
So, Raksha, just a quick question here. So, with the fact checking system, how do you validate this? I'll give you one example. So, yesterday I was browsing the Instagram. So, I belong from Bihar, Madhubani. So, there was a claim in the picture says Mount Everest Himalaya is visible now from Madhubani after 100 years. So, I got a bit skeptical. कि maybe it is possible. So after 100 years that has come. So I have validated on Google 2, 3 images I have sent. Then it got. So how at the back end this thing works? I would like to know. How do you validate the fact from which all sources?
Yeah, so fortunately, we in current time, from last 3-4 years, when this problem became very prevalent, we are having fact checking websites also. So there is one fact checking website by Aaj Tak, which verify their own news as well as news by other channels also. So if we post the news, there are many fact checking websites. If we just Google it, we will be able to get the link, and we post the news, or there is option to upload the image also, because most of the time the news is associated with an image, which is actually a fact, which is actually an artificially created image, or image from some other event but associated to the text. So that is providing, we can say, some sort of annotated data set for us, or some sort of verification system to us. Another because it is like a very real time process that we are every day we are witnessing, the way you exemplified, every day we are witnessing fake news. So another clue comes from the historical data also. So even if your system is trained on historical data, and you are giving your news as input, just by seeing the combination of words, the way you interpreted that this cannot be possible, I cannot see Himalayas from this particular place, from historical data, system will be able to learn that these words never occurred in context of each other. Then how can it happen today? So from historical data also we can get.
But if something is new, I will come to the most another exciting example. Have you seen these days one news where one meteorite has fallen in one of the country, and a guy has taken a debris and some random creatures is floating in the lake? So this has never ever happened. Someone was saying it's AI generated. Although when I cross checked it and I verified it was genuine video. So prior to that, there is no historical data for that. So in that case, how do we validate if the news is entirely new? No historical record exists. Never such incident has happened before. Then how do we validate such things?
Yeah, you're correct. Actually, if that is something new, and that is factual also, it has really happened, then it is so this can be considered as a challenge, because here historical data cannot help. We will need manual experts to verify the news. So that we can say, that's why when it comes to machine learning models, we say that they can never give 100% accurate results. Because for such cases, they may fail. Here, historical data, the data which is in our hand, that that will not help. In fact, it will produce wrong output if we give this kind of incident to be predicted as false or true.
Okay. Okay. Thank you.
Yeah. So what can be the data sources? Yeah, in continuation to the previous discussion, that there can be other components also which can help us to identify or validate whether a particular news or post is fake or not. So if we are gathering data from multiple sources, instead of relying only on the post or tweet or comment or review, which is user generated content, then we are having like, share, followers, watch time, how many times it is watched. Okay, so if somebody is giving like dislike most of the time, so probably they have verified it, and they have or probably they belong to that region and they verified it. No, it did not occur in our region, so it is a dislike. They might not have written it as a comment to the post, but they have given a dislike, and many such dislikes are there. Then there is a clash between the post and the response which is coming from the users. Similarly, shares, if there is no share, even no matter how exciting the news is, okay, how unique the news is, but there is very few shares, that is also that may also become an indicator. Okay. And then other factors like what social graph I share in social media platforms. So that can also be an indicator. If in my circle, if there are many people who are who share genuine news, who do not have any history of sharing fake news, or who shares fake news, who do not have who has this background, like most of the time our news is labeled as fake news, that can also become a good indicator. So follower following pattern, which is also similar kind of input, which can provide similar kind of input. If the person whom I am following, he or she himself share fake news, then there are high chances that I will also be doing the same thing. Okay, and instead of relying only on the textual content, we can include videos, associated memes or images that can become the source of data. And location and temporal data. So what time a person check in to the system, or during what time stamps he or she was there. Trending patterns, if something is trending within a certain duration, or just now something has started trending and I am posting news related to that trend. Okay, for example, there was Me Too movement just overnight. It started trending, and many things starts trending. Then there are high chances that there will be fake news also associated to that particular topic of trend. So fake news detection or misinformation detection can be considered as a simple classification problem statement by machine learning algorithms. One simple naive approach can be you implement a logistic regression classifier if you are having labeled data, and you can use any mechanism to represent your data in machine readable format. It can be term frequency, inverse document frequency, or it can be bag of words based model. So this is like traditional way. Um, in terms of more recent approaches, we are having bidirectional encoders, which can give you better representation of words from the corpus. So instead of just relying on TF-IDF representation or bag of words model, we go by bidirectional encoders representation. So where our idea is that if we can get better representation of words, we can get better classification. And this representation is not limited to the corpus. We can use pre-trained encoders like BERT or variations of BERT that can give us more meaningful representations. Now, more recently, we have seen use of decoders, which are having two components. They generate representation of words as well as they produce language or new words for us. So decoders have a mechanism of decoding the words also for us. So we can use the output of decoder also to perform this kind of classification, whether a news is misinformation or a legitimate information. But the biggest problem associated with pre-trained large language model, that is, they are licensed tools. We have to pay a cost beyond a certain version. We have to pay a cost for using them. And if your data is multilingual data or multi-model data, then again, it will be challenging for large language models to produce the output. And another solution can be combination of BERT and decoders, which have provided like cutting edge solutions, or we can say state of the art solution for fake news detection, where BERT provides representation of the documents and decoder finally based on the processing of the output of BERT and uh, and by combining this information with decoder's mechanism or decoder's attention layer output, it is able to produce classification output for fake news detection. So here, when we are combining BERT and decoders, we are seeing this advantage that we are bringing two types of complementary information together. One is by BERT, which are such models trained on excelling or giving very accurate representations of words or document. And decoders are such models which are trained on generating new words or new content from the existing content. So we are trying to combine two different types of learning mechanisms and which are able to give complementary information, and we are able to see the output, either it is comparable to the output of the large language models if we are able to fine tune large language model. On the other hand, if we compare the output of such combined encoder decoder models, they are able to outperform LLMs which are not fine-tuned, because fine-tuning also has its own cost. We have to tune billions of parameters, which is not the case when you are having your encoder decoder system, which you are training from scratch within the source data set. Okay. So now let's discuss about the working of transformers. So we have already discussed the use of encoder decoders. So transformers can be considered as decoders because the task on which these models are trained, that is generation of words. It can be next word prediction, it can be masked word prediction, but here we are trying to that overall training of the model is happening on generation of new word at the output layer. Okay, so transformers we can assume like we can keep them in decoders category. And the first architecture of transformer was given by Vaswani et al. In their paper, Attention is All You Need, where they try to emphasize the importance of attention layer. So the goal of transformer is not new goal. This was the goal which was targeted by Mikolov et al. Also in 2013, that you develop a system which is able to generate representation of words in the form of dense vectors. Okay, it should not be sparse vectors. It should not be direct word interpretation as we do by bag of words model. It should be dense vectors, and the representation or the vector should be learned such that it is having information of the context words. So this idea was named as a distributional hypothesis, though distributional hypothesis is not a new idea. It was introduced around 1950s by many linguists, but we started using distributional hypothesis in machine learning, or we were able to see vector representations based on distributional hypothesis after the major work which was done by Mikolov et al. In 2013 in their research work. So goal was same when Vaswani et al. Discussed transformers, but they introduced two new things. The first was that not all context words have equal linguistic relationship with each other, which was not the case with word-to-vec model or global vectors. They were having this intuition that all words have equal relationship if they are occurring as a context words. Okay. So that is different thing that they will get different weights when we are targeting some task at the end layer or at the output layer. But in the beginning, we are giving equal importance to all the words. But that should not be the case, because word may have more attention, or they may look to few words in their context to define their own meaning or to learn their own representations. So it should not be equal distribution. It should be dedicated to each word's location. Second idea was that a word having rich linguistic relationship may be far away, pervades language. Okay, so if we talk about word-to-vec model or global vectors, their context window size was very small. Okay, we started with a context window size of 5, and we experimented with 10 or 20. Actually, we were limited by the resources also. That was also one of the reason. But now with the advent of very high processing graphical units, we do not have that constraint, and we are having cloud systems also available where we can globally run our experiments. We do not need any local system. So we can increase our context window size also. So what Vaswani et al. Highlighted in their paper, that a word may have linguistic relationship to learn its own representation with a word which is far away. So a context window can be of size 32,000 or more than that. In fact, millions of words may be there in the context window. So that was one additional feature. So two linguistic properties they tried to incorporate. First, that not all words are equally important to get the representation of a particular word at particular location. Second, a word may depend on another word which is far away in the context. It is not necessary to be within a context window of size 10 or 20. So these were the two linguistic properties they tried to capture. Another thing was that another contribution was learning was in terms of implementation of these two linguistic concepts by attention layer. So they introduced a new layer which was called as attention layer, and in a regular deep neural network which was trained for generation of new words, or we can say which was trained for language modeling task, but they inserted a new layer that was attention layer. And the job of attention layer was, the primary job of attention layer was to learn attention score with for each word against all context words. It can be unidirectional, or it can be left to right context, it can be bidirectional context, or it can be mass context, depending on what type of transformer or what type of language model you are referring. So the fundamental transformer model, what Vaswani et al. Presented, that was a causal language model. When I say causal language model, I mean the context was read from left to right. Okay, so if my input word is, yeah. So if my input word is it, or by input I mean I'm targeting the word it to learn the representation by a transformer, then context words will be all the words behind it. Okay, that was a causal language model where words were read from left to right to learn the representation of the current token. Okay, so all words like because, road, the, cross, didn't, chicken, and they will become the context of the word it. And the context window size can be a very big number. So there were few philosophies behind their idea that not all words are equally important. We give attention to few particular words. Okay, so there were few supporting philosophies like we remember those incidents more for which we pay more attention. So whatever happened in our life, we do not give equal importance to all the incidents. And that is the reason we do not remember them. Only those incidents for which we paid more attention, we remember them more. So similar kind of analogy was established to learn representation of word. Not all words are equally important. This particular word would have paid attention, more attention to few particular context words. Okay, some similar analogy was given in 1759 by Idler that the true art of memory is the art of attention. So if you want to increase your memory for a particular incident or for particular sequences of your life or incidents of your life, you have to pay it entirely depends on the attention. I may not be able to describe this statement very clearly, but roughly it means that you will be able to remember or memorize those incidents more for which you paid more attention in past, and that will define your memory, how much attention you are giving to each incident. So problem with word2vec and global vectors, which were also having the same objective that giving representation of words, they were giving static embeddings. By static embedding, we mean that there was only one embedding with respect to each word. Okay, and which is not the case. If you are giving a static embedding, in such scenario, in fact, there are many such scenarios. I'm giving just one example from Professor Juravsky's book. The chicken didn't cross the road because it was too tired. So here the word it may refer road or it may refer chicken. Okay, but when we see the context word like tired, we realize that road cannot be tired. Who would have been tired? Chicken would have been tired. So it, the representation of it should be bind with the representation of chicken. It should not be bind with the it should not be bound with the representation of road. So here we can say, while learning the representation of it, the more attention should be given to the word chicken, not to road. There can be some contribution of road, but not as much as chicken is contributing. So if we are giving equal importance, we will get such a representation of it, which is not very meaningful. And that will hinder all the problem statements wherever you are applying this representation, whether you are performing fake news classification, or you are doing sentiment classification, or you are training a language model again. So, or you are implementing a translation system, everywhere this will hinder. This generic representation of it will hinder. On the other hand, if we are having representation of a word, which is different for all occurrences of it in the corpus, and the representation depends only on the context words which are having attention or higher attention to this particular word. So such embeddings or such vector representations were called contextual embeddings. Although we were using this term contextual embeddings at the time of word2vec and global vectors also, saying that our representation of a word depends on the context words. So they were also called contextual embeddings, but the term contextual embedding got more meaning and now it is like valid to associate with these kind of embeddings with transformers, where a word may get multiple representations depending on the context, and context may vary throughout the corpus. Okay, so for example, bank is a very ambiguous word. We have seen many examples. Pushpak sir also used to give example of bank while teaching word disambiguation. So he used to exemplify river bank or financial bank. So it was hard to, when it was limited to linguistic approaches, or when it was limited to simple traditional machine learning approaches, it was hard to differentiate between river bank and financial bank. But if we go by contextual embeddings, where all the words which are having higher attention with a river bank, these all words will be very different from the words which are occurring in context of financial bank. And the good thing is that we have flexibility of learning multiple representations of word bank. So earlier we were having this kind of information in the form of WordNet kind of resources, where manual annotators were sitting down and associating different meanings which are possible for a particular word. And they were giving the context words also to make us understand that a word can occur in different, with different meanings and with different context words. But when we allow contextual embeddings to be learned, and it can be different based on the different context, we have overcome that limitation. Okay, so for river bank and financial bank, we will be learning two different embeddings, and they will be very meaningful embeddings representing these two senses of the word bank. So there are two more examples indicating the same idea that we are in need of two different representations of the word it. Okay, and it is possible with contextual embeddings. It is not possible with static embeddings like by word to vec. The chicken didn't cross the road because it was too tired. The chicken didn't cross the road because it was too wide. So in both the cases, it is referring to a different word. In first case, it is referring to chicken. In second case, it is referring to road. And this clarity came from the context words like tired, wide, and we can consider chicken and road also. But since we got this flexibility that you can learn two representations, depending on which context you are coming across, we are in good state. Similarly, it gives other types of information also. For example, R is a plural word that can be defined if we are able to learn representation of R based on the current context words. The keys to the cabinet are on the table. It is indicating that R is a plural. R is used to assist a plural word. So the overall inference is that such contextual embeddings or these kind of representations are able to give us proper meaning of the word. And even in such situation where the words which have higher attention or highly tied with the current word or current token whose representation has to be learned, they are far away from the current input token. Even in that situation, contextual embeddings can give us better representation, which can actually improve the performance over end task like language modeling or classification, and which we have witnessed also as soon as we saw transformers. We applied transformers in many NLP tasks. They gave state-of-the-art results because of this fundamental property that a word may change its meaning or representation when it is used in different contexts. So there should be dynamic embeddings. So transformers provide this kind of solution by giving attention to a long context window. Okay, so first is it will generate dynamic embedding. Second, it will generate embeddings considering a long context window. So these are the two features to capture the two linguistic properties which we discussed. So transformers, if we see the architecture, it appears like a deep neural network only, except that in between, we are having a stacked transformer block. And in the transformer block also, most of the layers are same as the deep neural network layers. We are having one pooling layer, we are having one normalization layer, we are having one output layer or softmax layer, but there is one layer which is new layer, that is attention layer. Okay, so we are having, if you see in between, there are blocks in blue which are having stacked transformer blocks. So we are having, it is showing four layers, which is nothing but different layers of transformers. Okay, and all four layers are in combination. So one of the layers between them is the attention layer, and rest are like normalization layer or simple feed forward layer. So the novel thing with transformer is that, so here we are considering the base version of transformer, which was presented by Vaswani et al. That if we consider the word thanks, okay, so thanks will be interpreted as initial embeddings from using some embedding matrix E, and we will combine this representation. We will simply add this representation with the positional embeddings also. So 4 is representing that it is the word is appearing at position 4. Okay, so when these two embeddings are combined, the initial embedding of the word thanks and the positional embedding for the word thanks, we get a new representation in the form of X4. So X4 will be supplied as input to the transformer block where there are multiple layers of transformers. Depending on which model you are using, which model of transformer, it may vary from if you are using ChatGPT, if you are using Llama, if you are using BERT, the number of layers may vary. Okay, so base BERT and in fact, the variations of BERT are having different number of layers of transformer. So each layer, what it will do, it will take input from the previous layer. So if I call this layer as k plus 1 layer, then previous layer will be called kth layer. It will take interpretation or output from the previous kth layer, as well as the kth layer of the transformers belonging to the context words. So for thanks, the words which are occurring at third location, second location, first location. So here we are showing window of this much size only. In reality, it will be a very big context window. Again, depending on model, which model you are using, the context window may vary. For large language models, we are having context window size of millions of words. So this is the kind of arrangement, and at last at output layer, we are having simple feed forward network, which has one unembedding matrix. So unembedding matrix does nothing but converts the output of the transformer block into the desired dimension of the vector, the dimension of the vector which we want, and which is passed to a softmax layer or a logistic unit, depending on what is our expectation. So in this case, we are trying to implement transformer as a language prediction model or a large or a language model. So we are having a scope of seeing an output of vocabulary size. So, but one of the node will be the winning node, which will give the highest value for the predicted word. So in case of thanks, the next predicted word is for. And in case of and, the next predicted word is thanks by the model. So we are having one unembedding matrix at the output layer through which our vector or the output of the transformer block will be passed, which will be converted into a probability vector or such a vector which is in desired dimension, as well as it is interpretable to a particular word from vocabulary. So this architecture is for left to right transformer, but we are having variations of this. Yeah, so the first architecture which is shown here, this is the similar architecture what we have seen in the previous network, and it is called a causal language model, which is having self-attention layer only. And the second diagram is for a bidirectional self-attention layer. So here, what I'm trying to do here, I'm trying to just show the self-attention layer network, which is, so only one layer I have taken, which is having um, attention layer associated to each token and generating attention distribution, which are represented in the form of A1, A2, A3, A4, A5, which are nothing but representation of X1, X2, X3, X4, X5, but they are having this information, which word from the context is more important to me or more important to define my representation. Similarly, in case of bidirectional self-attention layer, it will be two ways arrows. Okay, so arrows will be coming from forward direction as well as backward direction. Yeah. So so the tokens, the initial input words like so long and thanks for, they come from a subword token system. So there are algorithms which we can use to generate tokens, because the entire output of your transformer model will depend on how good tokenization system you have. If your word is tokenized wrongly, then your system, the generation of the representation also will be erroneous. So we are having three popularly used algorithms for tokenization purpose: byte pair encoding, word piece algorithm, and sentence piece unigram language model. So depending on which algorithm performed better for which system, we are having their uses in different setups. For example, BERT relies on a particular type of tokenization algorithm, and Roberta relies on a particular type of tokenization algorithm. So we are having variation among them. But the purpose of all the tokenization algorithm is the same, that we want correct token for which representation has to be learned. You can write your own tokenizer also if your data is like straightforward data, and if it is in English language, then writing a tokenizer is a little easier. Unlike Dravidian languages or many other foreign languages also, like Chinese, which are having their words mixed as a single word. So although we have discussed this while seeing the architecture, but I'm taking you through the steps of the transformers transformer model one by one. So at the initial state, what we will be doing, we will be first generating tokens using tokenization algorithms. Once we have tokens, we will be using some standard embedding metrics. It can be a randomly generated matrix, or it can be a matrix from existing models like word2vec or global vectors or fast text embeddings. It is up to us. It can be experimental also. You can play with different embeddings after knowing their theoretical background. And once we have embeddings of words available, embedding metrics available, we combine these embeddings with positional embedding to form the input to the transformer. So we are at this stage where we have got x1, x2, x3, x4, x5. Then to generate contextual embeddings, what transformer is going to do, it will learn contextual embeddings by integrating the representation of the input token with the contextual words. Okay, and since it is integrating and it is having multiple layers of transformers within a block of transformer, as well as it is taking input from the previous blocks also, which are belonging to different context words, these embeddings will be very informative embeddings. It will get richer and richer until it reach the final layer of the transformer block. So how does the binding of the network happens? We compute representation of token I by combining information about token I from previous layer with information about the neighboring tokens from the previous transformer blocks belonging to I-1, I-2 up to the context window size. So what do I mean here? So when we have to bind this network, the representation of X4 will be combined with the first layer will take representation of X4 and representation of X4 minus 1, X4 minus 2, X4. So if this is our ith token, then I minus 1, I minus 2, I minus 3, and so on up to the context window length. All will transfer their input to this particular layer, which is responsible for generating the initial input or combining input for X4 and other context words. Now, how this combining, the term which I'm using, that combining the input or integration of input is happening, that happens in a very systematic manner that is called attention mechanism. We do not simply combine representation of X4 with X3, X2, X1. We have some attention mechanism which works on this principle that if we have to learn the representation of it at layer k plus 1, we will take input of it from layer k as well as a representation of it from layer k, which is the previous layer, and we will try to learn such representation of it which will be more dependent or which will have higher attention with chicken, the, and the word like road, which are actual contributor in representation of it, or representation of it should depend on them instead of other words like because, cross, didn't. How it actually happens or mathematically happens, this happens, what do? We try to learn attention distribution. So attention distribution is nothing but a vector representation again, which is saying that how much attention should be given to the previous context words or context words which are following me, which are following the current token. So what do? We try to compute at layer k plus 1, we will see all the input from left to right, which is a causal or autoregressive setup. And we will take inputs like x3, x2, x1, one by one. And we will try to see the similarity with the representation which is coming for the current input token. So if our targeted token is X4, what is the similarity of X3 with X4? How much is the similarity of X2 with X4? How much is the similarity of X1 with X4? These similarity values will actually give us the attention score or the final attention distribution. Let's see how does it happen. Similarity we compute by the dot product, which is the fundamental mechanism of computing similarity between two vectors. So suppose X3 is our target, and for which we want to learn the attention distribution. So X3 is here in middle, in between. So we are having X2, X1 as the context words. So we will be computing X3.X1, X3.X2, and X3.X3. Obviously, X3.X3 will be higher because we are computing similarity against the same word, but it is not going to harm us. Okay, because in any case, we have to learn representation of X3. So how much attention it is giving to itself, or how much information we already have about X3, that will be helpful to learn actual final representation of X3. But this information of X3 will be integrated with information of X1 and X2. So initially we learn the dot product between these vectors, and then we normalize this dot product by softmax. So these will be scalar values. These dot products will be scalar values. When we apply a softmax, they become a probability distribution. This probability distribution is telling you nothing but how much similarity other words, including the current word, is having with the current word, X3. Okay, so when we apply softmax, these probability scores we can interpret as alpha values. We call them weights also, or attention weights, which should be associated to words like X3, X2, X1. So once we have attention weights, we multiply this attention weights to each vector. So alpha 1 will be multiplied with X1, alpha 2 will be multiplied with X2, alpha 3 will be multiplied with X3, and their summation of these three multiplication will give us A1, A2, A3. Sorry, that summation will give us A3. But parallel computation will happen in all the attention layers. So we will be able to see attention distribution for all the words. So here is the mathematical representation, what we have discussed so far. So our job is to learn AI for a particular token at position I. A is nothing but a vector of size xi. So so our job is the first fundamental job is to compute xi dot xj, where xi is the targeted word for which we want to learn the representation, and xj is the all context words in causal modeling setup. J will be less than equal to I. So for all j's before I, we will be computing similarity score. Once we have similarity score, we will impose softmax, which will give us probability distribution. This probability distribution will become attention scores or weight attention weights alpha ij, which we will be using to obtain the final AI. So alpha ij will be multiplied with xj, where j is ranging from this is actually nothing but the context window size. So starting from beginning of the context window up to the token I, we will be having context words. So this summation will give us AI. So given a sequence of token embeddings like xi and previous context embeddings x1, x2, x3, x4, x5, x6, x7, we compute similarity score. Based on that similarity score, we obtain weights for each context word, including the current input word, and we produce AI, which is nothing but a weighted sum of x1 through x7 and xi. So AI is nothing but here we have written in words what is AI. AI is nothing but a weighted sum of x1 through x7 and xi. So in this manner, we obtain the representation of it, which will have more emphasis or more attention score for the word like chicken and road. So here the shade of blue is indicating like how much weight is given to a particular word. So here chicken has got more weightage in comparison to road and the. So what we have discussed so far, that is principle behind learning attention distribution. Attention distribution at a particular attention layer. We repeat this process in a stacked transformer blocks, and at the end we obtain a very good representation, very informative representation, because of two factors. One is that we were having a very long context window. Another factor is that we are repeatedly trying to gather more and more information from the same corpus. That is also playing a big role. We are not taking decision in one go, unlike Mikolov's model, where we simply try to implement a logistic regression model for classification purpose, and in one go only we try to obtain embeddings of words as weights of our classification model, which is not the case with transformer. So in terms of architecture also, they are very rich. In terms of context window size also, they are very rich. In terms of contextual, in terms of hypothesis behind the model, they are more informative. And that is the reason they are giving a state-of-the-art performance. Yeah, so in addition to this, we are having few more. When we say that we have to learn attention distribution, it is slightly more complicated. What we have seen, that is like raw maths at one layer. But when it comes to actual implementation, there are few more things like key and value matrices. With respect to each X, we are having key and value matrices. Instead of having just one word representation, we are having three types of representations. So here I was telling you that we are having initial representation in the form of X5, initial representation in the form of X4, X3, X2, X1. But actually we are having three types of representation for the same word. One as a value, one as a key, one as a query vector. But I won't be able to cover all this in today's lecture, but I have kept it in a very elaborative manner. If you follow it, you will be able to get, I'm not removing this content. Otherwise, you can consider this. So I won't be asking question from this part, but in case those who are interested, they can cover this part, these slides also, and they can get a good idea about um, transformer language models. And these slides are mostly from Zuravsky and Manning's book, the recent version of their book. And with my own idea, so to make it more elaborative. So these two types of transformer architectures we have already discussed, and we are having another transformer architecture, or we say that bidirectional transformer encoder, that is called BERT, which is popularly used from 2019 or 18, and it also gave a state-of-the-art performance. But the difference here in case of bidirectional transformer encoder was that they were trained on the objective was different. Here objective was to learn the representation of the word, unlike previous case where more emphasis was given on representation of the on generation of the words. Here more emphasis is given for representation of the words. That's why they follow masked language modeling instead of causal language modeling or bidirectional language model. What do? We mask a word in between and we try to generate representation of this particular word long at the output layer. Okay. So we try to generate this particular word only instead of generating the entire language or the next word in the sequence. What do? We try to generate only the masked word, which help us to be more focused on word representation learning instead of excelling on language prediction task. So that was the fundamental difference. Otherwise, in terms of architecture, they were, in terms of working, they were more or less same. Okay, I think we can stop here. I can take this last topic also, fine tuning of a pre-trained models. So you all would have witnessed, although you all would have implemented also, because I'm sure Pushpak sir or other instructors would have given you such problem statements, or in your project also, in your assignment also, you would have considered such problem statement where fine tuning of a language model, which is a pre-trained language model like BERT. So when you fine tune, the model becomes aware of your data set and your task. So that starts performing better than the raw version or the actual version of the model. So what do we do in case of fine tuning of a pre-trained model? So idea behind pre-trained model was that instead of training a model from scratch and wasting your resources which are available at your end, what do? We use the existing models and fine tune them, and it is very cost effective solution. And in addition to that, you can get results which are better than your own trained models, because these pre-trained models have seen a huge amount of data set which is hard for us to gather or to collect. Besides this, in terms of number of parameters also, they are very rich models. So what do? We take a pre-trained transformer network, which will have very rich contextual word representation capability. We will add a neural network classifier as a head. In this scenario, we call the neural network classifier as a head after the top layer of the network. So the network which you have seen here, we will take exactly the same causal language model, and we will impose one more layer of neural network, which we will call the head of the network. And that layer will be according to the task on which we want our model to be fine-tuned. So for example, if you want to fine tune on a binary classification task, then your last layer can be simply can be a logistic classification layer, or a network which is having sigmoid function at the neuron. So what do? We put a top layer of we put a layer on top of the existing pre-trained model and train the entire network. Not only this layer, we will be training or updating the existing weights of the entire network by using a small amount of label data on the downstream task. So for example, your task is a fake news classification system, and it is a binary classification task. Your last layer simply may be a sigmoid layer, and it will be tuning the parameters of the entire model such that the prediction on the task or prediction on the existing handful data should improve. And we can do the same job for other settings also, like named entity recognition or language inference. This fine tuning is considered as a transfer learning task also, because we are transferring the knowledge from the external source to the local system, which we are training on or which we are fine tuning on a local task of our interest. While pre-trained model was designed for a language generation task, or it can be a masked language modeling kind of model also. Okay, now I can take questions. Any question?
No, ma'am, there are no questions from class.
Okay, how many students are enrolled in this class?
So there are more than 120 students enrolled in this course. Yeah. Most of them are here in classroom.
Okay.
Yeah.
All right. So although I have already shared these slides, but I will share the updated version. I have made some changes in the PPT, and in case you have any doubt, you can ask over email, or yeah, you can ask over email and referring the slide number in case you are going through it later. Uh, if you want to stick to, you do not want to cover the query key part, but that is also very informative content. But in case you do not want to cover, because I'm not going to ask question from that content, but I'm keeping it for the sake of completing the topic and giving you complete information about the transformer model. And in case you want to go through, they are very self-explanatory. You can go through on your own.
Okay, sure, ma'am.
Okay. Yeah.
Okay.
Thank you, everyone. Bye.
Okay, thank you so much. Yeah.